Hey guys, today we'll be proving the central limit theorem. So the central limit theorem states that if we're given a set of n IID random variables, the standardization of those variables, so just subtracting the mean, dividing by the variance, converges in distribution to the standard normal distribution. So more formally, this it looks like um, having IID random variables with finite mean or with finite variance and therefore finite mean, and then have Zn equal these random variables minus their mean over the sample variance, and then we should have that our Zn converges in distribution to Z equals standard normal. And so to prove this, we will take a strategy of first showing pointwise convergence in our moment generating functions of Zn, and for the moment generating function of Z, and then we'll apply Levy's continuity theorem, and this will therefore, given pointwise convergence of moment generating functions or even characteristic functions, Levy's continuity theorem shows us that our random variables then therefore converge in distribution. So this is the kind of strategy we're going to take, and um, then we can kind of just get started. So we can start with our moment generating function of our standardized random normal variables, or our standardized normal random variables, and we can say that this is the same as the expectation of e to the s times Zn, which is the same as, if we spell out Zn, um, the sum of our random variables minus n mu by root n sigma. And this just comes from the fact that when we do our standardization, xn minus mu by sigma by root n, we can just multiply the whole thing by n, and we can get the sum of xn minus n mu by root n sigma x bar n. Or not x bar n, but and so the next thing we want to do is we want to do kind of what I call the log sum trick. So the log sum trick is that the product of the logarithmic of individual terms is the same as the log of the sum of those terms. And similarly, well, first we will actually want to, before we actually invoke this trick, let's actually next kind of clean this up. S by root n sigma, the sum when k equals 1 to n of xk minus mu. And so this is actually a much cleaned up form of our exponent, but we can notice instead of summing in the exponent, we can take the product in the root. So, and that's very, very closely related to log sum trick. And that's es root n sigma, but the product from k equals 1 to n of that xk minus mu. And then by independence, we can actually move our expectation on the inside. So now we just have the product from k equals 1 to n, the expectation of e to the s by root n sigma x k minus mu. And since these are IID, the distribution of xk is not changing at all, so this is actually the nth product of the expectation. So we can just rewrite this as expectation to the nth power of e to the s by root n sigma x minus mu. Because all x's are the same, they're identical, independent, they're independent and identically distributed. So now we kind of have a pickle. We have some value that is an exponential that might be pretty hard to compute, and then we take its expectation and then raise it to the nth power. Kind of what we can note here actually is that e to something is the same as the Taylor expansion of e to the x. So e to the x Taylor expansion is this, where it's just x to the I over I factorial, and we can just take the Taylor expansion of the terms and then keep the expectation and then the power on the outside. So expectation of 1 plus x squared over 2 factorial, 1 plus x squared over 2 factorial plus da 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 da. We can just say that this is, okay, s over root n sigma x minus mu plus s over root n sigma x minus mu squared over 2 plus, and then we can just call this higher order terms. And we have this expectation, and then we raise the expectation to the nth power. So now let's bring expectation inside. Expectation of 1 plus expectation of s by root n sigma of x minus mu plus s squared over 2 root n sigma expectation of x minus mu squared plus higher order terms, expectations of all of those, but they might go away, and then all to the nth power. So expectation of 1 is 1. This is just doing the mean square of our value, so that expectation of our random variable minus its mean is obviously 0. Then expectation of the mean squared. Okay, well, we kind of know by definition that's our variance. So we'll have 1 plus 0 plus s squared over 2 root n sigma times the variance of x plus higher order terms, all to the nth power. And here, okay, I missed a square here. The square should apply to the denominator as well. So 2n sigma squared. And the variance of x we know is sigma squared. So then this now ends up equaling 1 plus s squared over 2n sigma squared times sigma squared. And all to the nth power. And if we kind of do some more simplifications, 1 plus s squared over 2 by n to the nth power. And we know this converges to e to the s squared over 2, because it is a fact that the limit as n approaches infinity of 1 plus a to the n converges to e to the a. So now we just have shown that as n goes to infinity, our moment generating function converges pointwise to the moment generating function of the standard normal distribution. And then now by Levy's continuity theorem, we have that Zn converges in distribution, and I can just write my conclusion, of Zn of S converges pointwise to M of Z of S. So therefore, by Levy's continuity theorem, Zn converges in distribution to Z equals, and that then completes our proof.